So today we're going to talk about quadratic functions and models. All right, what are quadratic functions? Let's start with a definition. Let a, b, and c be constants with a not equal to 0. Then a function represented by f of x equals ax squared plus bx plus c is a quadratic function. This is generally referred to as standard form, though not in every textbook. Frequently, for me, I refer to this as standard form. Notice that a can't be 0 because if it were 0, then the x squared would be canceled out, and then it would just be a linear term. All right, so what are some terms and facts that deal with quadratic functions and models? First of all, the graph of every quadratic function has the shape of a parabola. The leading coefficient a tells us a lot about the graph. It tells us if a is positive, the graph opens upward. If a is negative, then the graph opens downward. All right, pretty straightforward so far. The turning point is called the vertex. All right, so we have a vertex here and here. And if a is greater than 0, the vertex is a minimum. And if a is greater than 0, if a is less than 0, the vertex is a maximum. The y-intercept can be found at the point 0, c, because when x is 0, 0 squared is 0, 0 times a is 0, plus b times 0 is 0. All I'm left with is c. So we know the y-intercept. And there's a vertical line called the axis of symmetry that passes through the vertex. Now, since it's a vertical line, it will have the equation of a vertical line, and it will be of the form x equals. All right, so our axis of symmetry is always of the form x equals. And it acts as a mirror, so the left side of the parabola should be exactly the same width, the same dimensions as the right side. If we ignore the sign of a, so we're looking at the absolute value of a smaller a makes the graph wider, and so a lot of times we'll think of these as values less than 1. We'll say something like 0 is less than a is less than 1. So smaller graphs make smaller values of a makes the graph wider, whereas larger values of a make the graph narrower. And we'll talk more about that when we talk about transformations. Other than standard form, we also have vertex form we use quite frequently with parabolas. The parabolic graph of f of x equals a times x minus h all squared plus k, with a non-zero, has a vertex at h comma k. Its graph opens upward when a is greater than 0, and downward when a is less than 0. The a in this formula is the exact same a in the standard form formula. All right, exact same one. So what we can do with this whole idea of the vertex form is we could write the equation of the graph that's given here in vertex form. So what do we need to find? We need to find our vertex. And it looks like this point here is the vertex, and that point is at -1, 3. So I know that h equals -1 and k equals 3, which allows me to substitute. We have f of x equals a times x minus a -1 all squared plus 3. Keep in mind, subtracting a negative, we can simplify this. That's f of x equals a times x plus 1 all squared plus 3. But we don't have everything yet. We need to find this a. Now, to find a. And so we'll go over here and do that. In order to do so, we're going to find another point on the graph. It can be any point at all. This one right here looks the easiest to me. It's the point 0, 1. So I'm going to use an x value of 0, a y value of 1 in our formula in order to find a. So I'll have 1 equals a times 0 plus 1 all squared plus 3. 1 equals, 0 plus 1 is 1, 1 squared is 1. 1 equals a plus 3. And if we subtract 3 from both sides, we'll get a equals -2. Once we know a equals -2, we could write our equation f of x is -2 times x plus 1 all squared plus 3, and that is our final answer. So knowing the vertex, we could substitute for h and k. Choosing any point on the graph, we can find our a value. And if we wanted this in standard form, we would FOIL x plus 1 times x plus 1. We'd multiply those together, distributive property. Then distribute the negative 2, and finally add 3. And we can find the standard form of that graph as well. All right, the vertex formula. So it'd be nice if we could find the vertex easily with the standard form as well. And in terms of what we were just talking about, given the standard form, our vertex can be found at negative b over 2a, comma, the function value at negative 2 over ba. So what we're saying here is the h value from the vertex form is the same as negative b over 2a. The k value is what you get when you substitute the h. Right? It's the y value that goes with that particular x value. So even in standard form, we could find the vertex pretty easily in order to possibly rewrite in vertex form. In this case, my vertex h will be negative 7 over 2 times 1, right? B is the coefficient of x. A is the coefficient of x squared. This is 7 halves. The k value is the function evaluated at 7 halves. 7 halves squared minus 7 times 7 halves plus 5. I'm going to give us some more space here. I am going to correct this a bit. I need an eraser. I don't have my eraser. That's all right. I'll just put it in here. And use a white pen. Do I have a white pen? Of course I don't have a white pen. We're going to ignore that right there. There we go. I knew my eraser had come back. All right. And when we're evaluating this, as we're doing this, check it out. Square 7 halves. That's 49 fourths. When we multiply, if you need to, write down your denominator of 1 so you can multiply straight across. When you multiply straight across, you get minus 49 halves plus 5. You know, the nice thing about the vertex is it gives you hints along the way. So when you find the 7 halves, if you evaluate by hand, and it's in standard form, the first number should be exactly half of the second number, and they should have opposite signs. If that's true, then you have correctly found the x coordinate of the vertex. When I add these two, I'll always have the sign of the middle one, and it turns out to be the value of the smaller one. All right, sign of the second one, value of the first one. Let's see why that is. If I have 49 fourths, and I subtract 49 halves, we could put that into a fraction form, and we have the negative 49 fourths. So that's a little cheater's rule for you as you go forward. When we add 5, it's negative 29 fourths, and I'm going to trust it. In terms of fourths, 5 is 20 fourths, so when I add 20 to a negative 49, I'll get a negative 29 fourths. And we have now the vertex form. The a value here is 1, so the a value in my vertex form is 1. Frequently, we do not write 1s out in front. You can, but it's not considered correct math form necessarily. And there we have vertex form. So let's do another one. Let's do another one where the a value isn't just a 1. So my vertex, my h value, is negative b over 2a. That's a negative 6 over 2 times 3. That's a negative 6 over 6, which is a negative 1. My k value is 3 times negative 1 squared plus 6 times negative 1 plus 2. Negative 1 squared is 1. 1 times 3 is 3. 6 times negative 1 is negative 6 plus 2. Notice the first number, 3, is exactly half of the second number, 6, and they have opposite signs. So when I combine them, 3 minus 6 will be a negative 3 plus 2, negative 1. So my vertex is at 1, 1. No, it's not. It's at negative 1, negative 1, which will make my function equal to a, which is 3, times x plus 1 squared minus 1, because when I subtract a negative 1, it turns into addition. All right, let's do one more. Let's make this one in purple. So the vertex form, notice my C value is 0. That is not purple, that is brown. Yes, I do know my colors. So my H value, negative b over 2a. B is a negative 1, so negative negative 1 over 2 times a negative 1/2. Negative negative 1 is a positive 1. 2 times a half is 1, negative. Purely an accident between the two. My K value is negative 1/2 times a negative 1 squared minus a negative 1. Negative 1 squared is 1. 1 times a negative 1/2 is a negative 1/2 plus 1. Notice half of the second number, opposite signs. The result will be the sign of the second, positive, the value of the first. Negative 1/2 plus 1 is a half. So my vertex is at negative 1, comma 1/2. And my function can be rewritten. A value, negative 1/2. I don't know what that line is for, so let's take care of that. Go back to brown. Times x plus 1 all squared plus 1/2. Vertex form from standard form. But we can actually write vertex form in other ways as well. We could complete the square to write in vertex form. And completing the square, this is how I'm going to do it. And there are many different ways of doing it. This is just my method. So on my method, my first step is to get everything with an x in it on the right. And the function, and you could call this y if you prefer, so in case that x bothers you. Function notation, I'm going to add 5 to both sides just to kind of clear it out. Now I'm going to take half of 4 to get 2, and then I'm going to square it to add to both sides. So I'm going to take f of x plus 5 and x squared plus 4x. I'm going to square 2 to add 4. When I add 4, I add it both places. So on the left, I'll now have f of x plus 9. On the right, I have exactly the right value so that I can factor into a perfect square, binomial, a binomial squared. And subtracting 9 from both sides, I can now have my vertex form. Keep in mind, negative b over 2a, that's exactly what this is. Negative b, no, that's not. Never mind, I lied to you there. Negative b is negative 4 over 2 times a. Negative 4 divided by 2 is a negative 2. That's the x-coordinate of my vertex. If I put negative 2 in, negative 2 squared is 4. 4 times negative 2 is negative 8. 4 and negative 8 is negative 4. Add negative 5 to it, we get negative 9. So our vertex form is correct, whether we use the vertex and do it, or we complete the square. Let's complete the square again. Let me see if I can get what I need here. There we go. Let's use actual purple this time. So I'm going to take the 7 to the other side. I'm going to leave some room. I'm going to take half of this 10. And then I'm going to square it So I'm going to add 25 to both sides. On the left, I'll have f of x plus 18. On the right, I've added exactly the right thing, so I'll have x plus 5 all squared. Finishing this out, I can rewrite my function as f of x equals x plus 5 all squared minus 18. From standard form to vertex form to standard form, there we go. So let's do some application problems with quadratics. A baseball is hit so that its height in feet after t seconds is given by s of t equals a negative 16 t squared plus 44 t plus 4. How high is the baseball after 1 second? Let's evaluate this by hand. I know that s of 1 is negative 16 times 1 squared plus 44 times 1 plus 4, which is negative 16 plus 44 plus 4, which is a negative 16 plus 48, which looks like a 32 feet in the air. All right, after 1 second, the baseball is 32 feet in the air. Find the maximum height. How are we going to find the maximum height? Think about it. Maximum leads us to a vertex. And I notice that I have a negative leading coefficient. So with a negative leading coefficient, I know my graph opens down. I know that the vertex is the maximum height. So the height of the baseball is s. The seconds is t. So the t value will be at negative b over 2a, which is a negative 44 over 2 times a negative 16. That's negative 44 over a negative 32. Two negatives, when they're divided, will give us a positive. It's at 1.375 seconds that the baseball will reach its maximum height. Its actual height, s, I'm going to go ahead and find this on the calculator. We have negative 16 parentheses 1.375 squared plus 44 times 1.375 plus 4. Hopefully I entered everything incorrectly, and we will end up with a height of 34.25 feet as the maximum height. And we could check this with a graphing utility, whether you use Desmos or I have a calculator emulator here. Whatever system you use, you can check and make sure that those values are correct. All right. A rancher plans to fence a rectangular area for cattle using the straight portion of a river as one side of the rectangle. Somebody forgot a period. That was me. All right, so we have this river. And along the straight portion of the river, we're putting up fencing. And my fencing is always brown. So I'm using the river as an edge. This is not a good idea. Cattle are not afraid of water. They'll cross. Just saying. Especially if it's a New Mexico river. They're a little dry sometimes. All right. If a farmer has P feet of fencing, so the perimeter of this, let's call this Y. We'll call this Y. Why would I do that? How about we call these X's and a height Y. So we know that the 2X's plus Y equals P feet of fencing. Find the dimensions of the rectangle that give maximum area. So the area of a rectangle will be XY. We want maximum. Anytime we see maximum, we're thinking vertex or calculus. Since this is not calculus, we're thinking vertex. So I'm going to solve for Y in terms of P. So we don't know what P is. We can't use just a 40. We can't use a 17. We can't use a specific number. It's a generic P value for our fencing. So when we substitute in here, we'll have X times P minus 2X. Area equals minus 2X squared plus PX. So we have our area written in terms of a quadratic that faces down. At its vertex, we'll have a maximum. So the vertex is negative p over 2 times a p over 4. So find the dimensions of the rectangle. I want to know my dimensions. That's my answer. So the x value is p over 4. I can find my y value, p minus 2 times p over 4. This is p minus 2p over 4. That is p minus half a p. Look at that. They work out. And that's 1/2 p. So my dimensions are the width should be p over 4 feet. And the length should be p over 2 feet. If I wanted to know the actual area, I can multiply these together to get p squared over 8 for the maximum area. All right, quadratic functions and models, that is the end of this lecture.